kind of joint are you talking about here with wind?
A seismic joint.
But a windy seismic joint?
Yeah.
Extra strong Roman concrete.
Fully hydraulic.
Structural welded connections.
It's the
Structural engineering podcast.
Welcome to the Structural Engineering Podcast. My name is Max.
And my name's Zach.
Hey, and this week we're talking about building separation joints.
Every joint you got.
Keeping buildings away from each other. Seismic separation joints, wind separation joints, I guess. That's less exciting. And then a little bit on sort of masonry separation and different materials. So that's what we got. What do you think?
I'm fairly excited.
Okay.
Yeah.
Okay.
Yeah.
Before we get into these separation joints, we got a tip of this day.
What is the tip of this day, Max?
The tip of this day comes from me messing something up, which is kind of where a lot of these come from, actually.
Hey. Whoa. You can't take all of it. I mess some of these up too. Sometimes I mess up your tips. So
I wanted to talk for a second about Chapter 13 forces, which are seismic forces on non-building structures. So this is the type of force you would apply to something, let's say a partition wall or ceilings, cabinets, laboratory equipment, access floors, all sorts of stuff. And they've got a great table in Chapter 13 that gives you coefficients, an equivalent R value and this A value, and it is sort of an acceleration parameter. What I had done accidentally is I was sizing a restraint on a partition wall, and I went in and I saw partition wall, first thing that came up, and it was an alpha of 1, and it was a R of 2.5. So I just went on, did my design.
no.
What it actually is a partition wall that was supported below its center of gravity, a cantilever partition wall, it's barely different, but it requires 2.5 times more force to restrain this type of wall. The reason is alpha value is a 2.5, the highest end. So I didn't mess this up again. I wanted to read about alpha and about the R, and it's actually pretty simple. You could basically guess what any system is going to be once you just know what these things mean. So a lot of people might already get where these come from. R is basically a ductility. It's the same thing we're looking at when we're at a brace frame or any system that might have ductility. Something very brittle has a low. Our partition wall generally is pretty redundant. It's fairly ductile, not as a force resisting system for a building, but just to hold its own weight up, it's pretty good. The alpha value, I'm forgetting if it's an A or an alpha, so I'm just going to interchange that. Hey, past Max, it's definitely an A, and it's called the component amplification factor. It varies from 1 to 2.5. The RP is a component response modification factor that varies from 1 to 12. It's equivalent acceleration. So if you have an alpha of 1, you're looking at basically like PGA or peak ground acceleration. You're on the far left-hand side of the acceleration curve. It is moving the exact same speed as the building. You can get amplification. When you have a higher period or you're more flexible. So this cantilevered wall can sway in the wind a little bit here or sway with the seismic movement. So it can actually amplify. So anything that can move in that sort of order is going to be at the maximum A at 2.5. Once you know these things, pretty much any system, like something ridiculous, I don't know, a rock glued down, what is the force on that? You know it's not ductile at all, and it's going to move with the acceleration of the building. So it's going to be a 1 on both accounts. So I don't know. I just like that because I don't think I'll make that mistake ever again.
Totally. I think something you can say with so many things. It's like once you know, and if I remember correctly, I think there's something with like piping that has like an R value of like 12 or something like that.
What?
That's pretty wily. Yeah.
Right on. Well, shall we hit the topic?
Yeah. Let's jump into some building joints. I think, the first one that really jumps out and that I think is really important. All the joints are important for many reasons. Our architects know about jointing like no other for all their finishes, and they understand how important it is. But structurally, it's immensely important. So I think the first thing, Max, that we start off with here is seismic joints, and it's something that's important. You got to have that joint. So it is most frequently required, I'd say, between adjacent buildings, separate parts of one building, creating two buildings. There's some different reasons why you might want to do that on one structure, is have different seismic joints within it. Many reasons that maybe Max you know of.
Maybe first, Zach, will you even tell me why we need a joint?
Yeah, absolutely. So a seismic separation joint is there to prevent the two structures from hitting each other So what that joint is allowing is for those buildings to move independently of each other during a seismic event. Some cases, they're introduced into like a single building, let's say like an H-shaped structure, an L-shaped structure. Sometimes you'll put in seismic joints to make kind of your lateral load path or your diaphragm load path easier, better, more constructible. I'd say that's a lot where you have these like separate wings of a building where you create this separation.
Absolutely. And that's, from my understanding, a little more of an old-fashioned thing to do. In a really complex building with a lot of separate diaphragms that maybe break out into rectangles a lot easier. It's still something people do. I think it's kind of an old-fashioned thing from what I saw, is basically to take any L or H or stack of rectangles and just break it up into rectangles. At the time, this was before analysis was primarily done on the computer, and it was just a lot easier to place these joints at the convenient edges and not have to worry about the movement of the building.
And I think in practice where you see this most is when you're building up next to an existing structure, and it really can add up super quick. And depending on what code you're using, actually, the amount of joint you have can actually vary quite significantly. As you grow in elevation, that gap needs to grow larger as this building's deflecting more, or the two buildings, being able to collide. And so that can actually add up to what I've seen, very significant loss of floor area that would be able to be leased out.
I think we both saw this example, but I got dibs on reading it here. I'm just going to go right from the quote. The loss of usable space can add up to a ton of money. So, for example, in downtown San Francisco, office buildings sell for more than $200 a square foot. So if an owner wants to construct a 40-story building on a site with a 100-foot long side adjacent to another building and a 4-foot wide building separation, the loss of square footage would be worth, in 2005, $3 million, which is absurd. I mean, it's a ton of money lost, rentable space lost to just making sure these buildings don't touch each other. And a 4-foot wide expansion joint, that's pretty big, but that's reasonable. Oh, 40 stories. Oh, yeah, that's nothing. Never mind. I was thinking, that's pretty big. It's not big for 40 stories. That's pretty small.
It seems fairly small for 40 stories. I think I've done some 4-story buildings that have got just a little over a foot. So...
yeah, that's wildly small. Even 400 feet tall, 0.015, you got 6 feet you need, and then the other building needs about 6, which is a great place to add in. These aren't necessarily additive when you've got two buildings. When you've got one building and it's drift limitation, and same on the other side, if one can move a foot and the other one can move a foot, it's not exactly that they have to be 2 feet away, right?
Yeah, it's the square root of the sum of the squares.
That's right. So if we were 1 and 1, we'd be 1.4. Cuts it down a little bit.
Yeah, definitely helps you out.
There is a little bit more here. This is for buildings on the same property, or maybe you can get away with it when they're the same owner. But when you're up against a property line, you actually have to be the correct distance, your story drift limit, away from the property line. But the exceptions keep going now that you know how expensive it can be to have a big seismic joint. If you do an inelastic response to design ground motions, the code also will allow you to reduce that separation, or at least modify it to the new information you just got.
Oh, one thing I think is interesting too is the code specifically states that it is acceptable to hit the other building if it is not catastrophic. So and I think the perfect example is if you have floors that are offset. Again, I'm going to assume for this so it doesn't get crazy complicated, but I'm going to assume that both buildings are owned by the same person. So that decision has been made to allow that to happen. What I think is interesting is how do you transfer the record of that acceptance to the next building owner? But that's a whole nother topic. When those buildings are moving together, if the floor, let's say, hits a metal stud wall, that would not be detrimental to life safety. If that stud wall gets hit with a diaphragm and crumples, it's acceptable. And obviously, diaphragm can't reach over far enough to hit building columns or that's more than likely detrimental to life safety. But just being able to hit the other building and maybe break the veneer, or maybe there's something going on to where it's not actually going to be very detrimental. So I think it's an interesting note in the code.
There is a little haziness in the damage thing, though. The line from the commentary is, if the effects of impact can be shown not to be detrimental, the required separation distance can be reduced. So it certainly does imply that if you have something that doesn't affect the structural integrity of the building, it can be damaged. If you're looking at the resiliency side of things, you really don't want glass to be breaking off or your wall to be damaged to a design earthquake. Remember, the design earthquake is really only 2/3 of the maximum considered earthquake. So we're already reducing it. By using that amplification factor, we're bringing it almost back to the actual deflections we'll see. But, to an MCE earthquake, we're going to be deflecting a lot more. So there might be a good middle ground where it's, all right, to the design earthquake, we're not going to impact. A little bit more than that, to the full MCE value, we will impact, but it'll be non-structural components. And then beyond that, no touching.
Yeah. I think the big key is, as long as it's not inducing load into the other structure, you're good to go. I mean, crumpling a wall, that's going to eat the energy up, right? It's not loading the other diaphragm where, could potentially overstress the next building and be very catastrophic to life safety.
That's great. There are some good examples, though, sort of apart on what you mentioned, where two floor diaphragms don't line up. Tends to be the most damage. So you've got a floor diaphragm pounding into what might be the shear wall of another building. That's going to be way, way worse than two diaphragms hitting. There's a lot of acceleration when two diaphragms hit, so it's a lot of force to slow down that quickly, but you're not directly damaging the shear resistance of the other building. So I think the most damaging situations are where the floors don't stack up to each other.
Yeah, and I think it's a very per scenario, per what's going on thing as well. I mean, if you take a massive building with huge seismic shear forces at each floor and you hit a small building, that would very, if you induce that load into the other diaphragm, would very quickly fail this lateral system, that would be very detrimental as well. So I don't think I will probably ever in my career, and I would love to clip this part one day and say I have done it, but I don't feel like that exception is used very often. If you're listening to the podcast right now and you've used that, or you've heard of someone using that, please reach out to us. We would love to hear the scenario in which that happened.
Oh yeah.
So a little story of a project I heard of. It was two buildings downtown Portland that during a seismic event would have the potential to hit diaphragm and be catastrophic. What happened is, once you induce that load, it created one of the stories was very weak story, sheared the story very quickly and would be catastrophic to the building. These are super old buildings, and it ended up being different building owners, and they're trying to figure out who pays to upgrade these buildings to not have this issue. I think I was reading about it, and it was part of like the seismic upgrade of like unreinforced masonry. So I believe one of the buildings had some unreinforced masonry walls on it. It was a really interesting discussion to hear. I have no clue where this has ever gone or whatever, but to hear what would happen, who is responsible for that. And, the city obviously can't come in and do that. And it's super expensive to make building owners that didn't know about that, I guess as well. So I thought it was an interesting article to read about what would happen.
I think newer buildings almost pay the cost when they're being constructed next to older buildings. Older seismic code, which maybe we'll talk about right after this, had lighter restrictions on the gap. If you are constructing a new building next to one of those older buildings, you have to anticipate that the building is going to move a lot more than they ever thought it did, the original designers, plus your building's movement. Not only that, but buildings now are more flexible than they ever have been, basically a better system. If you look at a special moment frame or a BRB system, those things kind of move a lot. So anyway, the new building is eating the square footage because it's next to this older building that probably is right up against the property line. Oh, well.
Absolutely. That one too is per scenario as well. I mean, Yeah, I think there are some buildings, old buildings you could evaluate. Yeah, like let's say you had a chevron brace frame building. I mean, that thing's gonna be super stiff, and yeah, it's just so dependent. One thing that I see engineers make the mistake of constantly is thinking that if a building is controlled by wind laterally, that building no longer needs to have a joint. And that is so untrue. It doesn't matter if your building is controlled by wind, you still have to have a seismic joint. Even and with regards to that, when let's say you design a building with wind, it's gonna move in a wind event. That diaphragm is gonna move, the lateral system, the building's gonna start moving. I mean, you still need a joint no matter what is governing your loads.
Totally. What kind of joint are you talking about here with wind?
A seismic joint.
But a windy seismic joint?
So yeah. So let's say you're in Oklahoma, and well, now Oklahoma has some seismic stuff going on, but let's say you have a building that's out there that it is completely controlled by wind. Seismic wouldn't control anything, even if you use Omega on your collectors, like those aren't nothing. Totally seismic or wind controlled. Your building still has to be designed for that, or the gap between your building and the next still has to be designed for that seismic separation. You still have to look at story drift and make sure you still have that room. And I've heard people, again, mostly new engineers say, well, I left, we just need an inch between buildings, or we just need 2 inches because that's all it's moving during a wind event. And it's like, well, if you run the seismic values for the required story drift, or the building joint that's required seismically, you actually need to go bigger, even though it doesn't govern the design.
I gotcha. Yeah, I think building separation is definitely a case where it's worth tracking the seismic loads all the way through the building, even in a low seismic region, just so you have a good idea of the distance that you're going to need. That table 1212-1 is the allowable story drift, so you have to be under that, and a lot of structures are just going to be under that regardless, especially if they're wind controlled, but it's good to consider. I'll throw in too that you need to consider the diaphragm deflection and the torsion of the building when you're looking at the separation. It's not just, the movement of the centroid here, and typically you'll have some torsion in a seismic event, and certainly the diaphragm moves a lot more than the main frame. The maximum separation has nothing to do with the force in the building. That table 1212-1 only has 3 inputs. It's your risk category, your type of structure, and your height. But yeah, it doesn't matter if it's a wind force or a seismic force. Those aren't the 3 things that are in the table. The only thing you don't have to worry about is your amplification. So that hurts seismic quite a bit, where wind doesn't have it, but you still have the same separation.
Yeah, exactly. Just because your building isn't designed, I think this is just a really good general tip. Is just because your building is mostly, maybe all you do ever is wind design, mostly because everything governs by wind design. You still have to design your building for seismic, whether it's a high seismic region, or not. Low seismic, you still have to design for seismic loads. It doesn't matter. Your seismic load combinations with Omega still apply to a building that's governed by wind. Whether it controls, it's so dependent on your building, but I can guarantee you can find a wind-governed building where the collectors and drags are governed by seismic load combinations, including with your Omega. So I think that's a big one to put home for anyone. It is important to run through your calcs all the way to the ground with both loads, wind and seismic.
The other sort of shortcut is if you know what your seismic system is and you know what your Omega is, your wind needs to be, let's say you're a 2.5. As long as your wind must be 2.5 times stronger than your seismic would be for the same system. And you're usually looking at like an R of 3 thing here. So that's quite a lot, but it certainly happens in many places of the country. But it's a good, quick check at your R of 3 system, figure out what your Omega is, and that should be what your seismic should always be under. I know early on, for me, I would check seismic and base shear directly next to my wind and say, oh, wind controls, and then just keep on going. But if you're in a building that requires any sort of collector or anything, that's gonna get hit.
Exactly. And to discuss exactly where we are in the code, it's chapter 1212, drift and deformations.
I've got this cool table. We already alluded that buildings have gotten more flexible. 1 and 2, the code has gotten more stringent on how close buildings can be to each other. So this table kind of compares example projects in some way, but basically starting from the 1982 UBC, this example separation joint, depending on the case, would be 8 to 16 inches. Going to the 94 UBC, that same building would be 36 inches. Huge jump twice. 97 UBC, we're up to 45, and the 2002, the very first ASCE 7, you're at 48 inches. From the lowest end 8 all the way up to 48 in 20 years. If you were real old-timey, you might hear someone say that you need 2 inches per story height. If we're looking at a 12-foot story height, though, nowadays, and we've got our limit of 0.025, we're looking at 3.6 inches. That 2 might be all right for masonry or concrete structures, but that's not going to fly anymore.
Yeah, it's wild. I think it's just such an important thing to think about at all times.
I'm thinking about it right now. The flexibility thing makes sense if you think of old masonry structures and concrete structures that weren't detailed to be ductile. They are super duper stiff. They really aren't going to move that much. If they start moving the amount that we expect our modern buildings to move, they're gonna be in trouble.
Absolutely. Yeah, if any of you guys listening have experience putting new buildings up against really old buildings and have a good strategy on how you determine that joint, reach out. We'd love to share that with everyone, and kind of just drives you to being fairly conservative with that joint, really. So Max, we got seismic joints. I think it's fairly straightforward. It's right in the code. I think, now everyone understands, sure, you got to have some joint for your wind, but definitely still have to think about seismic. What other kind of joints are important for structural engineers?
For structural engineers. Yeah, we're talking about different types of joints now.
So Max, yeah, we've talked about seismic joints. Pretty straightforward. You apply it whether you have wind governing or seismic governing. I think pretty straightforward for everyone to understand and find in the code and really have something to follow on. Now, what other kind of joints do we have that are important to structural engineers?
Let's say expansion joints in roads. Hitting everything. That's not where you're even going. I'm looking at a picture of a bridge, so it popped in my head. But we've got masonry ones. That's another very common one. So masonry expansion joints for thermal expansion. These things are always expanding. The smallest a brick will ever be is when it leaves the factory, so it only gets bigger. In the same sense, there are seismic joints within masonry walls. So if you have masonry wrapping a corner, that needs to be separated so that when the two walls move, you don't shear off the masonry. So there's kind of a second half of seismic joints that are like internal to the structure. What else do you got?
I think that's mostly it. I think like super long buildings, you're going to have expansion joints in them specifically for the thermal expansion of the structure. There's some good rules of thumb for steel buildings. You see this a lot in big precast structures and mostly warehouses, I would say, where you get these really long structures. You got to put these intermediate expansion joints in. And the big issue really becomes, how do you transfer lateral loads? Do you have to have a double frame line or lateral resisting elements at that line? There is some detailing that you can find online and some common resources for those types of systems that do allow expansion and contraction to occur, but to also transfer lateral loads through that joint.
Back to this bridge picture I'm looking at, I think that's the best sort of mental image of these long buildings that require expansion joints. If you look at a bridge deck, right, a bridge is subject to all of the weather because it's not a furnished space. So the thermal expansion of steel over 100 feet can be pretty substantial. So these bridges build in these metal grates or rubber barriers so the steel can move on actual rollers. If you've ever looked underneath a bridge, it's pretty common to see sort of a tube of steel with a beam resting on it. I love that bridges used like the model idea of a pin and a roller. Like they have a real roller. I think it's so cool. But yeah, just it allows the bridge deck to expand, the girders to expand without putting any additional stresses into the structure.
Exactly. Taking out that internal stress. And the bridge is the best example. They also do this for wood diaphragms. if you have super long wood diaphragms, they suggest building in a joint in the diaphragm just for construction. And then as the building is enclosed and comes to equilibrium, you come back and you nail the diaphragm back together. And you can actually see substantial movement of your exterior walls if you don't do this. And I believe they suggest, I could be wrong on this, I believe it's every 80 feet or so for a pretty long building, or maybe it's 200 feet. We'll write that in the show notes.
Yeah. I've never heard for a wood deck diaphragm.
Yeah, for really long ones, they suggest, it's not required by code, but detailing in a joint just for constructability purposes. They found if you let's say you get rain on your deck or whatnot, and that plywood, or that usually it's OSB, swells a little bit, it will actually accumulate enough to push out your end walls. And so you'll have these weird, like, kind of angled walls at the end that can accumulate to quite a bit of movement. So they suggest adding like a 1/2 inch. It's actually an APA detail, and they suggest, I believe it's a 1/2 inch. You kind of create this split in the diaphragm, and then you put blocking under it and reattach it. So then, your diaphragm is eventually continuous, but for the use during construction, it wouldn't be.
Huh, that's pretty cool.
The thing that scares me, though, is what if no one ever comes back and reattaches it?
Yeah. Well, I mean, what if they don't bolt your brace and other weird mistakes?
Yeah, absolutely. I think that's part of, maybe our job to be able to make things happen to where, coming back to reattach your diaphragm is kind of a weird thing. But when you're putting your brace up, you're bolting it in place, or you're welding it and bolting it to then weld it, So sure, things can be missed. I think it'd be something where I would make that be a special inspection or something like that, to where it's going to get done.
Yeah. Well, I think diaphragm nailing is special inspection, I believe. Yes, it is, but only for tight nailing patterns. Hey, remember when that happened to me where someone didn't weld my brace?
Yeah, I do. I feel like I just don't want to give people more opportunities to, miss something that could be such a, very catastrophic. And
yeah, it's just, the more opportunities you have like that, I could see more chance for failure, but work well with your contractor, I guess. Communicate.
Yeah, maybe go out there, make a site visit for around the time that you want to, they're going to be reattaching it, or it's all communication.
Or like draw and spray paint a big arrow that says reattach later so they can't forget.
There you go, Max.
I got a side note here, sort of, and this is control joints, contraction joints are not expansion joints. We've got a lot of joints in our field. Two of the big ones that we see all the time, especially contraction when it comes to concrete, or control when it comes to concrete, they're not the same as expansion joints, of course, but I think those words are often interchanged a little bit. So it's good to remember which one you're talking about. Control joints are for a substance that contracts as it dries or cures or whatever. For concrete, those joints are so that you don't get crazy cracking. It has nothing to do with later expansion of the concrete, to heat. It is just so that when the concrete contracts, cures, you don't get cracks. So not related at all, totally separate.
That's a really good thing to distinguish between, for sure. Terminology is always thrown around and can get confusing, so I like that. All right, well, thanks for joining in this week. Hopefully you learned something about expansion joints and seismic joints. And if you have anything to add, please reach out to us on social media. We'd love to share any information you guys have to everyone else, and keep everyone learning and getting smart. So please share with your friends, your family, your colleagues.
One more thing, maybe a little favor to ask. One thing that Zach and I are really into is the design process, and we're currently working on an all-encompassing design manual that either new engineers can bring in, or when someone is designing a new material they can refer back to. And this would be sort of an interactive, material-specific design process manual that you can go through the steps, check things off, help plan out your time a little bit better. I don't know what this is going to look like in the end. Maybe something sort of web-based. We're just toying with it, but I would love to hear how you guys, some of the people with a little bit of experience, go through the design process from receiving the project, all the way to execution, design documents. How do you make sure you check all the boxes and provide the best deliverable? anything you've got. So this is definitely something we're going to provide for free. It's just to get everyone's efficiency as high as they want it to be. So our email address is down there in the show notes, and we'll schedule a time to chat on the phone. Thank you. Bye-bye.